Yeah.
Okay, it's
Yeah,
on.
it's on now.
I think she has a little bit problem with this computer.
Yeah.
Does not go downward.
Yeah.
The next slide. The speaker. Next slide.
Yeah, it can't go down.
Okay.
Yeah? It's
Yeah, I
on?
think it was just.
Okay. Well, the topic of my presentation is novel continuous flow synthesis and analysis of calcium phosphate nanomaterials for biomedical applications. Um, well, I have divided my presentation into the four main categories. First of all, I would talk about background information. What are calcium phosphates and how could you classify them? And then I would talk about experimental, my novel synthesis by continuous plastic flow synthesis method and how it works, and then characterization under the category of X-ray diffraction, transmission electron microscopy analysis, and in vitro cell analysis. And finally, I would talk about conclusion and future work. If you have any question, I'll be happy to answer at the end of my presentation. First of all, a brief introduction. What are bioceramics? Ceramics that are specifically formulated for the reconstruction of damaged section of the skeletal system due to their ability to form a stable interface with the surrounding tissue and perform as efficiently as the natural tissue. And there are three main types of bioceramics: bio-inert bioceramics, bioceramics which have minimal interaction with the human body once they are placed in the human body, like zirconia, alumina, and bioresorbable bioceramic. As you can see from the name, it can resorb inside the body and degrade. And for example, broshite is the example. Tricalcium phosphate is a good example of bioresorbable calcium phosphate. And then finally, bioactive bioceramics. Bioactive bioceramics are the ceramics which can interact with the human body once they are placed in the body. And the best example is nanohydroxyapatite, which is the field of my study as well. Okay, and there are plenty of methods in literature in order to synthesize hydroxyapatite, calcium phosphate, and one of the common method is the batch process for the synthesis of calcium phosphate. But there are lots of problems associated with the batch process. Batch calcium phosphate chemistry, it's really difficult to control, and it's time and pH sensitive and expensive as well. Unavailable chemicals because you can't use all the chemicals, different types of, and stoichiometric reaction takes days. And sometimes it takes 24 to 96 hours to synthesize nanohydroxyapatite by using batch process. And it's a long time. And stoichiometric reaction takes days. What happens if the power goes off? Because in this reaction batch process, you have to add continuously, you see, the ammonia or any base in order to control the pH. And scale up reaction is even very harder. We have recently invented a new continuous flow system for the synthesis of calcium phosphate, in which we can synthesize calcium phosphate within 5 minutes, which are phase pure and which have very small particle size, less than 20 nanometer, and with very high surface area. And these are the main characteristics of this continuous flow. And if you can see, the continuous plastic flow system is very simple. Everything in this reaction, it is inside the plastic. So that's why it's plastic flow system. You can see the calcium ion source, the pump 1 and pump 2. We pump the calcium ion and phosphorus ion, and they meet at the T-piece mixer. And it was connected to 8-meter long plastic tubing, which is called heat exchanger as well, where we can give the temperature of 80 degrees C, 70, 60, at ambient temperature, and the time it's from 30 seconds to 20 minutes. I mean, it depends on the product. You can get any product in 5 minutes, sometimes in 10 minutes, 15 minutes, up to 20 minutes, depending what you want or what you required for the particles. If you required larger particles, we have to give more time. If required smaller particles, you can give a quick reaction of 1 minute to 5 minutes, and you can get the final product at the exit in this beaker as a fine white suspension. Why we invented continuous plastic flow system? It's because it's a plastic system, plastic tubing with the pump, so it's really, really very low cost. Allow use of low-cost precursors. We can use any precursor in this process. Phase pure calcium phosphate with less chance for mistake in few minutes, so we don't need like hours to make calcium phosphate or nanohydroxyapatite. Tune the phase via reaction variables. We can change the time, pH, and temperature in order to control the particle size and surface area. Low chances of impurities because it's in plastic flow, so it's suitable for biomedical application. Actually, our group has expertise in UCL, Clean Materials Technology Group. We have expertise in continuous flow synthesis, but this is under supercritical conditions of high temperature and pressure. So now we invented this system in which we don't need any high temperature or critical conditions or pressure. So it's very simple, single step, very faster, control growth and less agglomeration, so it's really easy to scale up. You can see some important calcium phosphates we have already made by using continuous plastic flow synthesis. We have prepared successfully hydroxyapatite, and with the calcium to phosphorus ratio 1.67, we have prepared calcium deficient hydroxyapatite by changing calcium to phosphorus ratio and pH range, and then we have also prepared phase pure broshite, which is really difficult to make in batch process. And we have prepared bioresorbable bioceramic as well, which is beta tricalcium phosphate, dicalcium phosphate, and hydrous monatite. We have also prepared, and calcium pyrophosphates. These are the phase pure calcium phosphate, which we have prepared in just 5 minutes using the new technology, continuous plastic flow synthesis process. We have also synthesized iron-substituted calcium phosphate by substituting carbonate iron in place of phosphate by the substitution of silicate iron at the temperature 70 degrees C in just 5 minutes, and strontium in place of calcium. We have also prepared zinc substituted hydroxyapatite, iron substituted, iron 2 plus and iron 3 plus, and manganese. So these are all iron substituted calcium phosphates we have prepared using this continuous flow technique. According to ISO standards, we have seen in ISO standards that any hydroxyapatite which is stable up to 1000 degrees C, we can use it for biomedical applications. And according to this new process, if you can see here, up to 1200 degrees C, the nanohydroxyapatite we have prepared using continuous plastic flow synthesis, it is stable up to 1200 degrees C. So it means we can use it for biomedical applications. So you can see no decomposition of HA into other phases was observed even after heating at 1200 degrees C in air for 1 hour. So this observation can clearly show the superior high temperature stability. By tailoring temperature, pH, time, we can get any specific product with controlled particle size and surface area within no time. If you can see that graph, in this graph, you can see the temperature and time. So at 80 degrees C, within no time, just 30 seconds, we can get the phase pair product. At 75 degrees C, we can get in 3 minutes, and you can see 70 degrees C, we can get the phase pair products in 5 minutes, and at 65 degrees C, in just 7, and then at 60 degrees C, in just 10 minutes, you can get the phase pair product of nanohydroxyapatite and other calcium phosphates. Here are some TM images. You can see the particle size. It's around 20 to 25 nanometer in all these. So this is the reaction at 60 degrees C in continuous flow reactor in just 5 minutes. So in 5 minutes reaction, you can get the phase pair product, and with very small particle size, and particles are, you can see the highly dispersed. So here you can see we can use this for the stable coating as well, because it's really small and well dispersed particles. And similarly, this is the reaction at 70 degrees C and 80 degrees C for the same nanohydroxyapatite. And now the particle size, by increasing temperature from 60 degree to 70 degrees C, you can see the particle size from 20 nanometer, now it's around 80 nanometer. You can see there. And then by increasing the temperature from 70 to 80 degrees C, the particles, they are now a little bit more larger, and you can see the particle size around 90 nanometer. So it means by changing just the temperature and careful control of time, residence time, we can make required particle of either 20 nanometer, if you want 100 nanometer, even more than the larger particles. So by changing time and temperature, we can get any controlled particle size with surface area. We have also done some in vitro biocompatibility study, and you can see that's the commercial HA and HA60 we have prepared at 60 degrees C, nanohydroxyapatite particles, and at 70 degrees C, 5 minutes, and 80 degrees C, 5 minutes. And you can see these results that the cells can grow on the surface of hydroxyapatite and support the osteoblastic human cells. So it means we can use these cells for the biomedical applications, for further studies and biomedical applications. Well, because I have done some studies on batch process as well, and I tried to make broshite under the batch process, but I didn't make it because there were lots of problems in making phase pure broshite in batch process, because the reaction is very quick and spontaneous, and it can change. You can see the steps: spontaneous precipitation of HA in the first step in order to make broshite, dicalcium phosphate dihydrate, the formula is, and complete, second step, complete dissolution and HA growth, and then appearance of first nuclei of broshite. In batch process, because you can't control exactly the temperature and time, and you're adding base in order to change the pH. So it's really, and you don't know about the exact nucleation time when you need to stop the reaction, and you need strong stirring as well. So it's really hard to make products which are, you can say, the time sensitive or very spontaneous reaction they have. So in this case, according to this continuous flow system, I made this broshite only in 3 minutes time. In 5 minutes time, whenever I tried, I got impurities or hydroxyapatite with broshite, a combination of two, but in 3 minutes time, with a careful control of temperature and residence time, I made this successfully, the broshite, dicalcium phosphate dihydrate. And so this is the broshite, XRD of broshite, and then FTIR analysis also there. And by hitting this broshite, we can get the phase pure monatite at 300 degrees C. And by further heating at 500 degrees C, we can get another type, which is alpha calcium pyrophosphate. And at 1000 degrees C, we can have phase pure beta calcium pyrophosphate in this reaction by using continuous flow synthesis. This is the overall view of phase pure calcium hydroxyapatite and their properties made on continuous plastic flow synthesis. We get phase pure HA with the BET surface area 264 meters K per gram. And according to literature, this is the highest surface area ever reported in the literature using ambient condition without supercritical high conditions. And in batch process, the highest surface area for this is around 113 and 120. So this is the highest surface area with the very small particle size around 20 to 25 nanometer, which is also novel in literature. You can't see these results under ambient condition with the synthesis temperature 60 degrees C and in just 5 minutes residence time. And we have also get pure HA by changing the precursor solutions using different precursors. And again, by using different precursor solution like calcium hydroxide and phosphoric acid, we got almost the same surface area, high surface area, like around 254, and the very small particle size. So it means by changing the precursor solution or using different precursors for the nanohydroxyapatite under this continuous flow process, we can get the very high surface area and very small size particles. And then at pure HA, we can get at 70 degrees C, the particle size, it's now 195. The surface area is 195 meters K per gram, and the particle size increased from 25 to now 80 nanometer. And by further increasing temperature from 70 to 80 degrees C, and you can see the results as well with the TEM images, the particle size 20 nanometer, 25 around, and then you can get the 80 nanometer particle size and 90 to 100 nanometer particle size, and with the biological morphological images as well. And the particles, you can see they can grow on the surface of hydroxyapatite in all cases. So it means by applying different conditions, different temperature, and residence time, we can get the required particle size with different surface area, high surface area, and you can see the low surface area with large particle size, and then 113 meter square per gram with the particle size is around 95 nanometer. So we have also done iron substituted calcium phosphate, and here you can see the carbonate substitution. When we did the reaction with the 8 weight percent carbonate substitution, you can get the BT surface area, which is around 136 nanometer meter square per gram, and the particle size is around 70 nanometer. You can see the TEM images for that and morphological images as well. We have also done silicate substitution, 0.8 weight percent silicate substitution, and you can get the particle size 110, and with the BT surface area, it's around 163. And with magnesium substitution, you get 120 meter square per gram surface area, and with the particle size 70, and with strontium, you can get the 80 nanometer particle size, and you can see the particle size under the transmission electron microscopy and morphological images as well. So it means by using this continuous flow synthesis process, we can not only make a phase pure calcium phosphates with different calcium to phosphorus ratio under different pH, we can also do different doping or different ion substitution calcium phosphates as well. Surface modified calcium and strontium phosphate for biomedical or dental application. We have also collaboration with some dental hospitals as well, and we did some dental, you see the restoration studies as well, and we use these particles, we coated the particles with different organic acids like methacrylic acid and vinyl phosphonic acid, adipic acid, methacrylic acid, and we use these modified agents in order to modify the surface of hydroxyapatite, and then we use this hydroxyapatite as a filler for dental composites. And we have also done radiographic images, and you can see in the case of strontium, the radiopacity investigation you can see here. So we can use this material for dental restoration as well. Here is the surface, high surface area hydroxyapatite. They are suitable for coating on biomedical implants because you can see they have very high zeta potential value, -70. So it means they can use for surface coating and for metal implant coating as well. This is the final view of in vitro cell viability study of pure and doped calcium phosphate made on CPFS. And you can see here with pure HA, 8 weight percent carbonated HA, silicon substituted HA, magnesium substituted HA, and silicon HA. You can see in all case the cells hydroxyapatite, they support the osteoblastic cell, you see growth, proliferation. So in conclusion, continuous plastic flow synthesis method is no doubt very beneficial over batch process because they offer many advantages. It's very fast process, having a very low cost, don't need a regular power supply. You can stop the reaction anytime. No special facilities needed. It can done in a closed flow reactor with reduced contamination. And by tailoring temperature, time, and pH, we can get any required product and with the controlled particle size and shape. Obviously, because they have very high zeta potential value and they are very highly dispersed, so there are less chances of agglomeration, so less agglomerated product, better defined shape, and we can easily scale up the reactor, which we are doing these days. We have scaled up already up to kilograms per hour. Future work, which we are doing these days, scale up plastic flow to kilogram per hour, which we have done now, and electrophoretic deposition. Suspension spraying we are doing these days, porous hydroxyapatite. We are making scaffold of these hydroxyapatite as well. And by doing packages and sterilization according to ISO standard, we can commercialize the product. We are in collaboration with the Polysciences from USA and Accentus from UK and with other different companies in order to commercialize our product. So I would like to acknowledge Professor Jawad Edar from Clean Materials Technology Group, where I did all my research work, and Professor Quentin Pankist from Institute of Biomedical Engineering, Islamic Development Bank for the scholarship, and University of Engineering and Technology, Pakistan. And thank you very much for your attention. So if you have any question, I'll be happy to answer.
Okay.
Actually, at the start, when I started my work, for the first year when I was doing my work, I didn't get any product which is phase pure. It was complete 1 year. I was trying to control the time, temperature. Sometimes I was controlling temperature and the time was not exactly the required time. And I did thousands of reactions again and again. And then finally, I got that, you can say, the magical conditions, like exactly 60 to 65 degrees C and 5 minutes residence time, because I tried 1 minute, 2, 3, and I was getting the impure material, which was not phase pure. So it was like all the time doing the same reaction, controlling one condition, second, third, and then finally I got that magical point or condition where you can get the calcium and phosphorus. They have spontaneous reaction and they got nucleation, and before they agglomerate or they, you can say the ripening of particles takes place, Ostwald ripening, agglomeration, I just take out the product and I just quickly did the further, you see, the freeze drying, and then I use the particles. So that's under the careful control of temperature, time, and then at the exact time, you see, to take out the product from that reactor, I did this. So it's really hard work to do this. And then finally, at the end of my second year, we filed this patent in October 2013. Yeah, so.
Oh, Linda.
You should use, which controls the size of your product. How does that affect the porosity of the feed?
Porosity.
How does the size, because it's made at a different temperature, affect the porosity of the product? In other words, is the porosity at one temperature and one size the same as the porosity at another temperature?
No. No, it's different. It's different. It's different temperature. Yes, it is different, a different temperature. So that's why, because you see, by changing the temperature just 10 degree from 60 degree to 70 degree, you can get the huge difference of particle size and porosity. So that's actually the magical conditions we finally found out that by changing this, we can change the porosity and particle size as well. By changing even a little temperature, 5 degree or 10 degree, we can get the different products at different.
Do you have any idea of what that range of porosity is over temperature?
Not exactly, yeah. So we would definitely, in further studies, we'll do that here.
Two more
Thank
questions there.
The use of the experiment on the dental field, you said. The dental field, you said.
Yeah.
Plant of the.
Yeah.
So you experimented or already it's in use?
No. We prepared this hydroxyapatite, and then we have a collaboration with the different hospitals. And then, because when they see the particles, because they're very small and very, you can say, with very high surface area, and they think that we can use it as a filler, because for dental composites, you have to have a filler which can come by surface modification. You can use it for the dental restoration. And when we use different, and then they said to us, use strontium substituted hydroxyapatite, because we can't see the image when we do the dental restoration. There are some issues of radiopacity. So can you use the strontium or silver, so that we can see the radiopacity image as well? So which in the commercial HA we can't do that. So we have to recognize the product. So can you use that? Then we did some further studies by using strontium and silver, and you can see it's really a good image, and you can see. So then they use it for the
Why I ask it? Because of the side effects. It's in the mouth of the patient. I'm asking about the side effects and for the allergy or whatever can come from this
No, we don't have, we have to definitely go for further studies. Either it is really good for that, because the thing is we can prepare any controlled particle. So we can mix them like the small particles and large particles. If you can see some dental materials, paper or these type of papers, they have the combination of particles for the dental restoration. So you can combine the small particle with high surface area and sometimes the large particles together, and then you can use as a filler. So that's why they were interested in it. And then in further studies, definitely they would see either, definitely in future.
Okay, one more question.
You mean the yield of the product? No. Size, not the amount, not the yield. Yeah. That's about the size. Because the reason is because at small, you can see at the less temperature at 60 degrees C. Because I did some experiment I started from room temperature from 25, and then I did at 30 degrees C, 35, 40, 45, 50. But I got the product, but it was impure. I didn't get the phase pair product. Then at 60 degrees C, I got the phase pair product. I think that because the reaction is very spontaneous, and at 60 degrees C, that the exact time when the particles, they meet together, they combine together to get to give you the product. And if you separate that product before they agglomerate or because the particles, they ripen, if you get the product, then you can use it, the particle size, because you are not giving them time to agglomerate. You are getting the product and you are doing further studies. And with giving temperature, you can see the particles, they have more temperature. So with the more temperature, the reaction, you see, the rate of reaction increases as well. So the particles, they have a little bit bigger size by increasing temperature. And with further increase of temperature, the rate of reaction increases. They have more time and they can agglomerate a bit. So that's why the particles, with increasing temperature, you can see the particles, they are increasing in size. But this is not the case with all, you can see the experiment. With the, when you are using the, you can say the organic acids or surface when you are doing surface functionalization, you can see by using that agents, you can control the particle even at high temperature, because you are using the controlling agent or the surface agent like organic acids. Even at 70 degrees C, we can get the small particle size by using surface modification reaction, small size. So it means there are some method in which you can control even at high temperature, you can get the small particle size by using any modifying agent or organic agent in order to control the particle size.
Okay, thank you.
Yeah, okay.